Hi, welcome to this particular module, and in last module what we have seen? We have seen bulk micro machining and surface micro machining, and then we have taken an example of using a bulk micro machining, how to create or how to design a process flow for fabricating a sensor for detecting volatile organic compound, right. So, in detail we have understood how each step can be formulated, right, to fabricate this particular device, right. And as you see there are multiple masks that we need to use to fabricate such a device. Now, what if I say that we need to still reduce the temperature? Now, you know, right, that what we discussed in last module is we have to use integrated heater to heat up the sensing material, correct. Now, this heater to reduce the power consumption to achieve a certain temperature, we are fabricating a diaphragm. Now, when we fabricate a diaphragm, instead of heating the entire silicon wafer, we have to heat only the diaphragm, thus the power consumption would reduce. But I would say that I still want less power consumption. I still want to have power consumption even less than what we can achieve through diaphragm. In that case, we need to use bulk plus surface micro machining. Right. So, how does bulk plus surface micro machining works, and can we design a similar sort of sensor using bulk plus surface micro machining, right. So, today we will see that particular part, and then we will see how about not to create diaphragm, because see there is some disadvantage. When you create a diaphragm, means we reduce the thickness of the wafer, the mechanical stability of the wafer also reduces. So, the sensor mechanical stability reduces. But what if I say that we can have the same mechanical stability, that means the thickness of silicon wafer and the thickness of sensor since the sensor that we have fabricated on the silicon substrate, the thickness is same, okay, thickness of silicon wafer and thickness of this particular device that is made using a technology that we will discuss, the thickness is same, that means mechanical stability is almost similar. But because of a slight change in the sensor technology, the power goes extremely low, and we can achieve a similar power consumption which we can achieve with a diaphragm. That means mechanical stability is high, power consumption is low, and still everything works perfectly. So, we will look at that kind of idea and the technology. So, let us see today, let us start our module by looking at bulk plus surface micro machining, right. So, yesterday what we have discussed? Yesterday we discussed this particular sensor, right. Today we will discuss this particular sensor. So, what exactly this sensor is? Now, you can see here, this is a hanging structure, it is a hanging structure, it is a cross sectional image, that is why you may not be able to see the hinges, but it is a hanging structure, and the thickness of the bridge on which it is hanging, right, is just 1 micron, only 1 micron thick, right. So, from a diaphragm that we have seen yesterday, which was about 100 microns, we are now talking about 1 micron. So, when we talk about 1 micron, right, the power consumption would be even less, power consumption would be less. So, what else this sensor consists of? Sensor consists of a heater which we have seen yesterday, then there is a sputtered silicon dioxide, you can see here, right, and then we have interdigitated electrodes made up of aluminum. Finally, we have a sensing layer made up of nanostructure zinc oxide material. We will see few SEM images of nanostructure material, how it looks like, right. And this pit is created using bulk micro machining. 5 micron pit is created using bulk micromachining. This is released with help of surface micromachining, right. So, we will see where bulk micromachining comes into picture, where surface micromachining comes into picture, and we have given this title schematic diagram of a low power MEMS based VOC sensor. Low power because it will have the heater will require less power to heat this this material, this much thickness of the sensing material, including the heater and the substrate, right, and of course your IDs. So, how can we fabricate this device? All right, let us see. Now, this if you see here, we have written 280 microns. Why not 500 microns? Because we are talking about a silicon wafer which is 2 inch in diameter. Okay, we are talking about silicon wafer which is 2 inch in diameter instead of 4 inch diameter wafer. So, this is the process flow, and we will see how to draw the process design of this particular process flow or how to design this process flow in the following slides. Right now, let us understand how we can get this particular sensor from a starting wafer which is our silicon substrate, right. As I said, it is a 2 inch silicon wafer. So, we have 2 inch silicon wafer on which we are growing silicon dioxide, right. How we are growing silicon dioxide? Using wet oxidation. So, now you can see this is a silicon wafer kind of grayish in color, right. After growing silicon dioxide, we can see green color, right. Now, using photolithography, we are creating a pit. Right. So, let us first understand how we are creating this pit from oxidized silicon substrate. Okay. So, if I just write down in terms of some numbers or some alphabets A, B, C, D, E, F, G, H, I, J, K and L. So, what we are looking at, how to create C from B, how to create C from B. Now, you guys are expert, right, in photolithography, right. So, you can draw a process flow quickly, is not it? We have oxidized silicon substrate, right. We have oxidized silicon substrate SiO2, SiO2, and this is our silicon. What we want? We want to have this pit. We want to have this pit, right. So, first thing is we will spin coat photoresist. We will spin coat positive photoresist. After spin coating photoresist, what is the next step? Next step is we will load the mask. We will load the mask. So, to open a window in silicon dioxide, right, so that we can etch silicon, right. We want to create a pit in silicon. So, for creating pit in silicon, we have to etch silicon. For etching silicon, we have to remove oxide from the area, right, where we want to etch silicon. SiO2, silicon, SiO2, photoresist, mask, correct. After that, of course, after positive PR, what we have to do? Soft bake, right. After soft bake, we load the mask, align the mask and perform UV exposure. UV exposure. After UV exposure, next step would be to develop the wafer, right, to develop the wafer. when you develop the wafer. When we say developing wafer, does not mean that we are actually developing wafer. Okay. It is called developing, we are developing photoresist, but in general we are dipping this wafer in photoresist. Let us say we are developing wafer, okay, but we are developing a photoresist. So, photoresist we have developed. Now, the unexposed area will get stronger, right, in the case of positive photoresist. So, the unexposed area is stronger, the exposed area is weaker, and we can see that the positive photoresist has been developed from the area which was exposed, Now, what is the next step? Next step is we have to dip this particular wafer in BHF. BHF is buffer hydrofluoric acid. When we dip this wafer in BHF, what we will get? We will etch the silicon dioxide, because it was exposed, right. So, silicon dioxide will get etched and we will create a window, right. Now, what is the next step? After this, the next step would be you dip the wafer. So, you can now remove photoresist, So, dip the wafer in acetone. When you dip the wafer in acetone, what you will have? You will have photoresist stripped off. When you dip the wafer in acetone, the photoresist will strip off, right. And then again the question would be, when you dip the wafer in BHF, with the back side will get etched or not, right. SiO2 on the back side can get etched. So, we can protect the back side by spin coating photoresist, So, you see here we have soft bake, then we have exposed, we have developed. After developed, we can spin coat photoresist on the back side and then hard bake, followed by removing the silicon dioxide through BHF, followed by stripping off the photoresist. Here we are with stripping of the photoresist. After that, if you dip this wafer in KOH, you etch silicon or TMAH, right, KOH or TMAH, and we know what is the etching rate. Of KOH and TMAH. Etching rate of what? Silicon. Etching rate of silicon, because these are silicon etchant. Then what we get? We get this particular pit, correct. This particular pit. This is the process. For creating a pit. Now, this is what kind of etching machining? We are using a bulk micro machining, because we have etched the wafer about 5 microns. You can see a pit of 5 micron meters. So, we are etching the wafer about 5 microns, correct. So, we are using bulk micro machining technique. Now, next step D. D would be to deposit zinc oxide and fill the pit and then planarize it by polishing, right. So, what we will do is easy, right. So, let us see here after this technique. So, we have oxidized silicon wafer with a pit, right, oxidized silicon wafer with a pit, in which we are depositing zinc oxide. This zinc oxide will act as a sacrificial layer. We will see why. Sacrificial layer. We are depositing zinc oxide on this particular pit, and then we are polishing it, planarizing it, planarizing zinc oxide. When we planarize it, when you planarize zinc oxide, then you get a relatively smooth layer of zinc oxide, right, zinc oxide. After that, what is the next step? After that, when you pit is planarized, right. So, what you do? You still keep on polishing, you still keep on polishing until you have zinc oxide left only in the pit, like this, right. So, now the pit is filled with zinc oxide. Let us draw zinc oxide in this particular pattern. So, we can understand that we have deposited zinc oxide, and now the pit is only consisted of is filled with zinc oxide because wafer is planarized. After planarizing zinc oxide, the next step is we will deposit a silicon dioxide on it. So, you understand this thing, zinc oxide, silicon dioxide, silicon dioxide, silicon dioxide, all right. Next is we will deposit nickel. Nickel for what? Because we want to create a micro heater, right. We want to create a micro heater. So, now you guys know, right. See, first is silicon, then oxidized silicon, then creating a pit, then filling the pit with zinc oxide and then planarizing it and depositing silicon dioxide, right. So, until these steps we are done. So, how many steps we are done? Let us see, A, B, C, D, E and F. We have just deposited nickel, correct. Now, what is the next step? From after depositing nickel, we have to fabricate micro heater. We have to pattern nickel to form a micro heater, right. So, where should we need micro heater form? Micro heater should form on the pit, okay. So, now we have this particular substrate. From here we need to create a micro heater. So, let us create a micro heater. So, I will just delete this, I will delete this and we will draw a process flow for creating a micro heater of nickel on the pit filled with zinc oxide and covered with silicon dioxide. So, let us draw here. We have a pit, and it is filled with zinc oxide, and then there is a thin layer of another oxide. Let us draw this another oxide in this particular fashion, and then we have nickel. So, nickel SiO2, 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 zinc oxide. Now, what we will do? You know, right? You know this step very fast. Positive PR, right? Next step, soft bake. Next step is what? Next step is load the mask, right? Load the mask. So, you should be now faster, right? You can see now I am slowly increasing the speed, because now I am sure that you guys understand what I am drawing here, correct. And then we have photoresist, and on photoresist we have a mask, and what kind of mask we have? We should have contact area outside the pit and the structure within the pit. So, this will be our mask, right. This will be our heater. Of course, this is what we are drawing is a cross section. These are heater pads, contact pads, contact pads. Okay. Okay. What we have done? So, we have mask, then we have photoresist, right. We have nickel, SiO2, 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 right, and here we have zinc oxide. After that, soft bake is already done, mask is loaded, we will perform UV exposure. After UV exposure, next step would be to develop the wafer, right, develop the photoresist. When you develop the photoresist, what will happen? Let us see. When you develop the photoresist after UV exposure, you will have right, you will have photoresist left in the area which was not exposed. After that, what you will do? Next step is to etch nickel, right. Next step is to etch nickel. So, where nickel will get etched? Nickel will get etched in the area which is not protected by photoresist, which is not protected by photoresist. So, this is what we will have. We will have nickel which is not protected by photoresist, you will get etched, and nickel which is protected by photoresist will stay, right. After that, what is the next step? Acetone dip, right. When we dip the wafer in acetone, what will happen? Photoresist will be stripped off and you will have a heater. Photoresist will strip off and you will have a heater, right. So, where are we? We have now fabricated a heater, right, on the pit, right. What is the next step? After this, if you see, after we have heater, next step would be silicon dioxide, right. We have to deposit silicon dioxide. So, let us deposit silicon dioxide on the wafer let me draw it here, is easier. This is guys bulk plus surface micro machining, okay, bulk plus surface micro machining. Right, and this is what we are at heater stage, micro heater. Now, we have to grow silicon dioxide, we have to grow silicon dioxide, right. Then what we have to do? We have to remove the silicon dioxide from contact pads. Why we have to grow silicon dioxide? Because next step is to form interdigitated electrodes, to form interdigitated electrodes. So, if I let us say have interdigitated electrodes in this particular fashion, right, then it works, but if I do not have this insulating layer between micro heater and interdigitated electrodes, then it will get short, right, because two metals cannot be deposited on each other or should not be deposited in each other for this kind of application. Okay. I am not saying it cannot be, a lot of applications requires deposition of multiple materials. So, this would be my silicon dioxide, right, this would be my silicon dioxide, this would be nickel, silicon dioxide, silicon dioxide, again silicon dioxide, zinc oxide. This is where we are. Now, next step is to open the contact, right. You can see here, the contacts are open, means the oxide is removed from the contact, window is created, right. Oxide is etched from the contact area. So, that we can you can see here very clearly, if you see this square, right, and if you see this particular part, then you can clearly see that the oxide is there and here the oxide is not there, right. If you see here, the oxide is etched. So, how can we do that? We know it very well. So, to do that, we will spin core photoresist, soft bake and load a mask such that the area which we want to expose, right, the area which we want to expose or the area which we want to etch will be exposed, and the area which we want to protect, that is our heater area, will not be exposed with UV light, since it is a positive photoresist. The contact area we want SiO2 to get etched, right. So, we have to remove photoresist from only contact area, and remaining area we should protect the photoresist. To do that, we will use the mask as shown here, and then we will expose the wafer with UV light. When you expose the wafer with UV light, since it is a positive photoresist, what will happen? After exposure, you will develop the photoresist. When you develop the photoresist, what you will get? You will get you will get this. What you will get? You will get a positive photoresist protected in all the area except contact area, you see, except contact area, right. Next step, what is the next step? To etch silicon dioxide. So, we will dip this wafer, in BHF. When we dip this wafer in BHF, what will happen? The silicon dioxide from the contact area will get etched, right. The silicon dioxide from the heater contact area will be etched. Next is we have to dip this wafer in acetone. When you dip this wafer in acetone, what you will have? Photoresist will be stripped off, right. Photoresist is stripped off. So, photoresist is stripped off, that means you have now micro heater contacts open, that means silicon dioxide is etched, right. So, where are we now? If you see, we are on I. Next step is, you see here, we have to form interdigitated electrodes, right. We have to form interdigitated electrodes. So, how can we form interdigitated electrodes? So, let us see. Now, we have silicon dioxide. So, what we will do? We will deposit aluminum using physical vapor deposition, right, and let us have pattern of aluminum like this. Now, what we want? We want interdigitated electrodes, right. So, same step, right. You see, once you know, it becomes so easy to use these steps, right. What is this? Positive photoresist. Then what we will do? We will soft bake it. After soft baking, what is the next step? Next step would be to create interdigitated electrodes on pit, right, and contact area can be outside. So, creating interdigitated electrodes on pit, we have to use a mask. What kind of mask we can use? We can use a bright field mask, such that it has the patterns for interdigitated electrodes, such that it has patterns for interdigitated electrodes. Right. So, what is this? So, let me just make sure what we are showing. This is aluminum positive here, this is mask, right, mask. Then UV exposure. So, when we expose this wafer with UV light, what we have? We have, when we expose the wafer with UV light and then we develop this wafer, what we will have? Photoresist protected in the area which was not exposed by UV. Next step would be to etch aluminum, right. Next step would be to etch aluminum. How can we etch aluminum? we can etch aluminum by aluminum etchant, by using aluminum etchant. When we etch aluminum, then what we have? We have photoresist, the area which was protected by photoresist, aluminum will not get etched, the area which was not protected by photoresist, aluminum will get etched, right. After that, what is the next step? Next step is to dip in acetone. When we dip the wafer in acetone, the PR will get stripped off, as you can see here, the PR will get stripped off, and you have your interdigitated electrodes. The PR will get stripped off and you have your interdigitated electrodes. So, what is the next step? Next step is, so you now we are here where we have interdigitated electrodes. Next step here is to deposit zinc film, right, by lift off and perform annealing. So, now you know, right, how to perform lift off? We coat everywhere photoresist, we coat everywhere photoresist, right. Then we use a mask, and a mask should be such that photoresist is protected in all the area except the area where we want to deposit the sensing layer, where we want to deposit the sensing layer, correct. So, if I use this kind of mask, this is my photoresist, right, this is my positive photoresist, this is my mask. I expose the wafer with UV light, I expose the wafer, right. What will happen? If I expose the wafer and develop the wafer, what will I have? I will have positive photoresist in this area, and this area is open, this area is open, right. Now, if I deposit my sensing layer, right, and after depositing sensing layer, if I dip this wafer in acetone, what will happen? The positive PR from all the area will get stripped off, right. When it strips off, the sensing layer over the photoresist will also get lift off, the sensing layer over the photoresist will get lift off, and if that happens, what will happen? If the photoresist gets lift off, then we have sensing layer only in this area, right, because photoresist will lift off the sensing area from rest of the area. So, this is our sensing area, sensing layer. This is our sensing layer, right. So, we are now having a sensing layer, you can see here. Next step would be to create a window, such that we can remove this zinc oxide. So, let me just draw everything and then we can create a window. Now, you know how to create a window, again using the photolithography. That will be our last step to fabricate this sensor. So, when you deposit sensing layer, you can deposit either zinc oxide, you can use indium tin oxide like we discussed, right. So, stay with me, okay. Is the last step. Now, you know what pattern is what, right. What we are drawing here is silicon dioxide, there was a micro heater, and then we have aluminum, right, and over aluminum we have our sensing layer. This is aluminum, this is our nickel micro heater, this is zinc oxide, silicon, SiO2, 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 right. This is our sensor. Now, what we have to do? We have to create a window, this area, 4 sides. You can see a top view here, you can see a top view here, right. So, we are creating a window on 4 sides such that, so now you know how to create a window, right. You deposit photoresist, you load the mask, then you protect the photoresist on all the area except the area where we want to create a window, right. So, if you just want to see, I can draw it, it is very easy. You see, what I will do is I will spin coat photoresist everywhere, right. Then I will use a mask and I will protect photoresist in all the area except this 2 area, right. This is a photoresist, right, and I will protect my photoresist in all the area except the area where I want to create a window. Why I want to create a window? Because I want to remove my sacrificial layer. I want to remove my sacrificial layer. So, to remove sacrificial layer, I have to use this mask, right. So easy, right. Now, you guys understand that how we are fabricating a sensor, right, or what is the process flow for fabricating a sensor, right. What we are learning here, same thing we can perform in the laboratory in a clean room. Okay. Okay. Now, if I expose this wafer with UV, this is a positive photoresist. What will happen? What will happen? The photoresist in area which is not exposed will be stronger. See, to create something takes time, to destroy very few minutes, right. So, creation is difficult, destruction is easy. So, try to create, not destroy. Try to always create the things. Now, you see here this is not what we will get, because we had window. So, let me just redraw it. right. We have created a window, you can see here, right. You can see here we have created a window. Now, what we will do? We will dip this wafer in BHF. When we dip this wafer in BHF, what will happen? We will have access to our sacrificial layer, right. We can now see the zinc oxide because we have etched BHF, right. We have etched silicon dioxide using BHF, right. So, now what will happen? If I, so first I have, after creating a window, I have dipped the wafer in BHF, which is buffer hydrofluoric acid, which will etch my silicon dioxide, right. And after I etch silicon dioxide, I can see through the through this window zinc oxide. So, now if I dip this wafer in 1% HCl, 1% HCl, this is my positive photoresist is protecting the rest of the area, right. Here it is not protected. So, if I dip this wafer zinc in 1% HCl, the zinc oxide will get etched, the zinc oxide will get etched, and you will be able to see a cross section image and our sensor is realized. But the positive photoresist is here. So, positive photoresist we have to strip off. How to strip off positive photoresist? We have to dip this wafer in acetone. So, when I dip the wafer in acetone, then what will I have? Then I will realize my sensor. Okay. Right. Now, my sensor is realized. So, we have sensor and you can see the role of zinc oxide in the pit was to act as a sacrificial layer. This particular way of removing zinc oxide, right, and is your surface micro machining, is your surface micro machining. So, we are combining bulk micro machining with surface micro machining to have a sensor with a on just 1 micron silicon dioxide, 1 micron silicon dioxide. This silicon dioxide that we have grown initially using wet oxidation is 1 micron. So, about 1 micron thick diaphragm or 1 micron thick bridge, right, we have created an entire sensor. So, where we are now? We are at the, we did this and we reached to our final sensor, that is what we wanted, right. We have realized the sensor by removing the zinc oxide, which was a sacrificial layer using 1% HCl. All right. So, once you have this, then what you will do? Once we have this, then what? Then we need to understand how the performance of the sensor, right. So, this is an optical photograph of sensor fabricated on micro machined silicon substrate. You can see micro machined silicon substrate, right, 100 micron diaphragm, and we are just, so this is 100 micron diaphragm is this structure, and the another one is our current sensor, which is using bulk plus surface. hanging, right. This structure, okay. So, if you see the performance, right, on 2 micron diaphragm, about 1 micron or 2 micron diaphragm, the for 100 watt, let us consider, let us 120 watt, about 120 watt for the sensor on 100 micron diaphragm using bulk micro machining, which is here, right, or which is here, we can achieve a temperature of approximately 120 degree centigrade, 120 degree centigrade. But for the sensor that is fabricated using bulk and surface micro machining, what is the temperature? About 300 degree centigrade, you see, 300 degree centigrade. Why? Because now the suspended diaphragm is only about 2 microns, and this is the figure for bulk plus surface micro machining. You get it? So, that is the advantage of fabricating a sensor using bulk plus surface micro machining technique, right. Now, this is how we have connected the sensor, right. Optical photographs of integrated MEMS based sensors. The sensor consists of a heater, interdigital electrode, sensing layer and a diaphragm. Either the diaphragm is fabricated using bulk micro machining or the diaphragm is fabricated using bulk plus surface micro machining. So, one is 100 micron diaphragm using bulk micro machining, or a diaphragm which is about bulk plus surface micro machining, right. A prototype packaged individual chip is shown here, right. Now, once we have this, we have to see what kind of sensing layer we will be using it, right. What kind of sensing layer will look like if let us say you are talking about nano, right. So, how can we have zinc oxide nanostructure, nanostructure zinc oxide. So, we will see that in the next module. In the next module, we will see how we can have zinc oxide nanostructure. So, till now what we have seen, we have seen a bulk micro machining technique, then we have seen a surface micro machining technique, right. We have taken 2 examples of designing a sensor or designing a process flow of a sensor, right. The first example was using bulk micro machining technique, and the second example was using bulk plus surface micro machining technique. Then we have seen if I have a heater on a bulk micro machined substrate which is about 100 micron, and if I have a heater on a bulk plus surface micro machined diaphragm which is suspended diaphragm about 2 microns or 1 micron, what is the advantage or what are the advantages? There are some disadvantages as well. What are the advantage? Advantage is that for the same power about 120 watts, for the sensor that is created on 100 micron diaphragm you achieve 120 degree centigrade, but for the sensor that is created on suspended diaphragm you achieve close to 300 degree centigrade. You see 180 degree centigrade more for the same amount of power when you reduce the thickness of the diaphragm, and it is obvious, right, because now the heater has to heat only 2 microns compared to 100 microns. So, the heat loss will be less, So, what are the limitations here? The cons, there are the pros we have taken, but what are the cons? The cons are that in suspended diaphragm the mechanical strength of the sensor is weak. Of course, compared to 500 micron, 280 micron, if it is 2 inch wafer, 280 micron thick wafer, if I am using 100 micron thick wafer, the mechanical strength is reduced, but if I talk about 2 micron wafer, the mechanical strength is tremendously reduced. So, we can have a better power, but the mechanical strength goes down. So, can you think of a technology where your mechanical strength remains same and still you can use less power to achieve higher temperature? We will be talking about this particular idea, how to use a slightly different technology, not really technology, but just idea, so that we can achieve a better mechanical stability, right. Also we will see how the nanostructure of zinc oxide can be grown with the help of a zinc metal, and to help you out that okay, once a sensor we fabricate, right, if we can fabricate lot of devices, then what? We have to interface those devices with electronic modules to get actual data. So, what kind of electronic module you can design to read the sensor output, right, because if you are looking at sensor output in terms of resistance, let us say. So, how would I know what is that resistance value and what that resistance value corresponds to which kind of VOC and what is the concentration of VOC? For an end user, he or she will be interested in looking at the value of that VOC, 10 ppm, 20 ppm, okay, that is it, not 10 kilo ohm resistance, 2 kilo ohm resistance, right, or capacitance. Output can be in capacitance, output can be in resistance, output can be in impedance. So, my point is whatever the output of the sensor is, we need to convert it to a readable format, right, from a end user point of view. So, you have to design electronic module. We will just take a very quick example of a circuit that we can use to interface with this kind of sensor to get a readable output, right. Till then you guys read what we have discussed in this particular class, right, and I will see you in the next module with the things that we have I have just told you. Till then you take care, have fun.